I guess I'll start. Hello, EPC. My name is Len, and this is Christian. Thank you so much for letting us join you today. It is a great honor to be in Breda and at EPC again, which is, of course, the coolest conference in the universe. Christian and I are both technical artists, and today, okay. Okay, I won't start that again, but yes, it is a great honor to be here. Christian and I worked on a game called Hyperlight Breaker, which I believe, thanks to our organizers, is playable outside. Is that right?
The only game playable, and that's because no one else set up the. I thought for a second.
Oh, you have no choice. This is the way our publisher would like things to be. You have absolutely no choice but to play our game.
That alchemy then it will.
So Hyperlight Breaker is the newest game from the game studio Heart Machine. Heart Machine is based in Los Angeles, aka Los Santos. It has developers all over the world, however, a small contingent in Los Angeles. This game, a Hyperlight Breaker, was made with a fairly sizable team. I think we fluctuated, but around 35 at our max. We had 3 formal tech artists and an engineer who worked on the procedural world that we're going to show you. Hyperlight Breaker is a successor, a kind of spiritual successor to a game, Hyperlight Drifter, that was our first title in 2016. I'm curious to do that kind of raise of hands things. Has anyone ever played Hyperlight Drifter? Awesome. Has anyone who here has played Hyperlight Breaker? Hey, okay, well, thank you for those 3 people. In Hyperlight Breaker, we basically wanted to create a successor. It's actually a spiritual successor because it's actually a prequel to Drifter. To give you an idea of what Drifter looked like, this is a trailer from Hyperlight Drifter, which in 2016 was a top-down 2D pixel art action game, RPG action game. And so it had a very stylized look and feel. And so when we wanted to create a spiritual successor to it in the form of Breaker, we wanted to create a very stylized game, not a realistic game that was inspired by the aesthetic. Here's a trailer snippet from Hyperlight Breaker. So the art style is inspired by Hyperlight Drifter. Hyperlight Drifter was made in Game Light Maker by about 5 people. Breaker, this game was made in Unreal 4.27. And maybe most importantly, for at least all of us here, that this new game was intended from the beginning to be an open world roguelike. It's actually a 3-person co-op open world roguelike. And like many roguelikes that came before it, it necessitated having randomized levels, ideally unique for every run. Whoops. That was not the way to go to the next thingy. Whoops. Oh yeah, here we go. Just trying to look at the rest of my notes, make sure I don't miss anything. But since the Breaker levels were basically open world experiences, we needed to create randomized worlds or randomized open worlds. And that's basically what we're going to be sharing with you today. Christian? Oops.
There we go. Am I coming through? Can you guys hear me okay? Excellent. So in Hyperlight Breaker, contrary to the procedural nature of the rest of the game, you actually start out in a hub space that is handcrafted, called the Cursed Outpost, where you can upgrade gear and buy and sell weapons and select your perks before traveling to the Overgrowth, which is the procedural portion of our game. Though little known to the player, as you're working through selecting your gear and choosing your perks in the background, the procedural systems are actually running to generate the world that you're about to travel to. Our technical target was to spend no more than 20 seconds building the procedural world each run. There's a huge amount of legwork and lifting from one of our engineers, Justin Beals, who took a lot of these initial processes and helped us put them into like asynchronous processes on a separate thread so that we could allow this to happen, especially on like our lowest spec target, which was the Steam Deck. Once you have your loadout ready, you jump on the teleporter and head down to the Overgrowth, which hopefully now won't be a long wait. Your first run through of the game, or the particular generated level that you're on, you start in an underground bunker, which is again a handcrafted space, but that's the last handcrafted space that you see before you come up to the overgrowth where everything is procedurally placed. This is one of the core approaches that we took to Breaker. The environment art team is able to create very directed and handcrafted assets that have some adaptability to them. And then our systems go through a bunch of data that we'll go over here that actually places them to create unique levels on each successive level generation. When you exit the bunker, there's a 1 kilometer by 1 kilometer world where you can move around freely. To any point on the map, I'll just keep looping this video here. But you can enter structures, pick up loot, get into scraps with enemies. There's 3 bosses per world who exist in these boss levels that are perched up on higher ground, typically up on hilltops for ease of visibility over long distances because the maps are pretty large. And each world is always made from 3 unique biomes from a total selection available of 4 biomes. Going over those biomes here, we have our forest biome, dominated by lots of trees and green grass and pretty rolling meadows. Our desert biome, again with very distinct art directions for each biome. We have our crystal biome, which is especially harkening back to the style from Drifter originally, and then the fortress biome. While it's a roguelike, you're expected to die a bunch. I did a bunch. I'm terrible at the game. But when you die, you resurrect back at the outpost and typically re-enter the same world. The game doesn't re-roll an entirely new random world as often as many roguelikes. I think we have a total of 7 tries that you can have for each generation or before a new world is generated. We want players to get to know the world a little bit and have the chance to explore it across several lives. The terrain is not generated at runtime. It's selected from a collection of pre-generated terrains built in Houdini. There's currently 25 in total, with more planned for the future. But the buildings, the ruins, those are handcrafted by the environment art team. And figuring out how to populate the world with them was probably the single biggest challenge internally. We called this set decorating, or decking for short, and this yields the fantastic name for our real-time population system, Hyperdeck.
Yeah. All right, so this is sort of like a really diagrammatic overview of how the system does what it does. So here on the left, we have all of the magic in Houdini, which is actually not that magical compared to what a lot of you are sharing with me today and during this conference. But it's basically generating 25 variants of terrains. Those also come into Unreal along with the mesh. There's viable positions, which we'll talk about in a second. A lot of texture maps that control where and how things get placed. And some non-random placements. So similar to PCG and Unreal, I saw a great talk yesterday at the master classes about bringing point clouds in from Houdini, and then you can reconstruct geometries in Unreal in specific places decided by Houdini. That's kind of the same idea. In the middle, there's this Unreal prep, and that's what we call the offline point process. And then finally, it moves data into the actual runtime, which is on the right. This is an interesting system, and I don't know if anyone else is doing this kind of thing, but what is going on here? This is probably one of the most mysterious things. There's a lot of interesting, difficult stuff happening there. But this kind of intermediate stage where we figure out what are all the candidate positions things can go in is because we had the constraint of 20 seconds of building the world in 20 seconds. And this needed to happen on our low-spec hardware, which was a Steam Deck. And so it kind of necessitated coming up with optimizations that otherwise might seem a bit clunky. Let's see. And in most cases, all the stuff this is Houdini with lots of Python. Almost everything happening here doesn't happen at runtime. It's offline, so that's mostly Python. And then everything that happens in runtime for speed was written, or rewritten at least, in C++. This is an example of an asset table. The way that we deck assets into the world, and again, I'm going to use that word decking. I learned it a few companies ago. I know it's not standard, but we use it all the time. So hyperdecking, that's placing assets randomly into the world, starts with an asset table. And basically, this is defining all of the rules that each asset needs to follow to be able to place itself into the world, hopefully intelligently. Probably the main thing we're trying to get at is we wanted to place assets in the world randomly, so it's random every time you go into the world, but it should feel as intentional as possible, like an artist placed it there. That was always our goal, and it's probably the goal of a lot of us here. In order to do this, we have this kind of intermediate stage, which is every row through this table goes through a process called point baking, and this is how it works. The first thing we do, step one, is we generate a dense scatter of points onto the surface of the terrain in Houdini. This scatter discards crazy positions we'd never want to put anything on, like steep cliffs, as well as exclusion areas. We call these bulk point lists, and they get sent over to Unreal. About 200,000 locations per terrain variant. And again, we have the 25 terrain variants we're talking about. And this is essentially pre-sampling the terrain, and it allows us to do things in Houdini that isolate certain or de-isolate certain areas or exclude certain areas, which becomes very important. In step two, a set of Python functions in Unreal iterates through every asset in that table. And for each asset, it then loops over every bulk point that you can see here. And this is just actually a small subsampling of the points. Obviously, there's not 100,000 points being presented there. So it looks and sees if any of those rules can throw out that point for that asset. So for example, if the asset is a beach-only asset, and it must be decked below a z-value of, say, 1 meter, which puts it on the sea level, the process will ignore all the bulk points with z greater than 1 meter for that asset. If all the qualities of that bulk point location satisfy that row's rules, then it becomes a potential decking position for that row. An index to that point is added to the row's array of allowable locations. If the point fails to satisfy all rules, it is skipped, and then the rest of the bulk point is tested, and the next bulk point is tested, and so on. So every asset tests all its rules against every point in this bulk point list. And it does take a while. The process results in a long integer array of indices referencing into the bulk point table. The system refers to these as candidate point lists, and we basically store them as a custom data structure in Unreal for efficiency. If you try to put them in a data table, by the way, bad idea. We did that at first. Data tables store these long strings for the row name, and if you try to put more than 100,000 things in it, or even close to 100,000, it goes bananas. So the whole process, this baking process, runs on a headless Unreal process running in Jenkins, and it takes about an hour and a half to refresh all the assets for all the variants. Point baking is necessary but painful. Every time the terrain changes, it needs a refresh. We also spend a lot of time tuning the rules for the assets to get worlds that look good to us and satisfy gameplay needs. The environment department is very good at reminding us when one of their beautiful temples or ruin structures is sliding off a cliff or floating in the air or some other problem with our decking. Or maybe there's simply not enough of them appearing. That's a very common problem that we had to deal with. And this tuning became such a core part of our development loop that we hired a technical artist, Randy Reynolds, who's awesome, to focus solely on asset tuning, and she quickly became a master of it. One thing that Randy did, which was awesome, this is a Unreal data table replacement. I don't know if you've done a lot of work editing data in data tables in Unreal, but they're not very flexible. They've got some nice features, but Randy, since she was going to spend most of her life working on this, wrote a really cool replacement for the data table editor. This is written in Python and Qt or Qt, and it runs inside of Unreal, and it provides a wide range of filtering and other kind of quick access. And of course, it's named Take it.
As Len mentioned, assets have a number of rules defining placement constraints and decking behavior. All the usual suspects are there, like slope ranges, heights, randomized scale and yaw, things like that. But there's also more complex rules like distance to nearest shore, closeness to paths, and flatness. Flatness in particular ended up being a very significant placement constraint for Breaker, mainly because the game features many large pre-made combat and/or exploration spaces that we call POIs, for points of interest. Decking large objects requires putting them in spots that have enough continuous flat ground for them. And since our terrains are pre-baked, we're having to evaluate terrain and flat spaces that are already there, as opposed to modifying the terrain to accommodate these pieces. Let me see here. Decking large objects requires putting them in spots that have enough continuous flat ground for them. Otherwise, they might hang off of cliff edges or expose, ugly underbellies or sides. To make a viable flatness check possible, we leaned into an Unreal-specific implementation of an algorithm commonly used for generating distance field data called jump flooding. And here's the first example when we learned how to generate jump flooding textures in Unreal. For anybody who's not familiar, the jump flooding algorithm was first introduced, and I'm sorry, I'm going to probably butcher the name, by Rong Guodong in 2006. It's a flooding algorithm that's particularly useful to us in generating distance field textures from various mask inputs. The algorithm, which was implemented as a series of shaders run through an execution process using canvas draw calls in C++, works by performing iterative neighbor pixel comparisons to get value distances, which culminate in a distance field texture output. For each iteration, as we can see on the initial image here, we compare the values of neighboring pixels in a 3x3 grid, excluding the evaluated pixel, but we store the coordinate of the neighbor pixel with the shortest value distance as opposed to the value. Each iteration reduces the distance of the neighbor pixels that we check against. So you see the orange pixels in the corner. Eventually, we're kind of like stepping them in towards the evaluated pixel until we're checking the values of the pixels directly adjacent to the evaluated pixel, which is a mouthful. An example of the output from the actual iterative process shown in the GIF here results in a UV advection texture, which we can use as the UV coordinates for the texture sample of the original texture, which gives us a dilation of the original pixels. And if you take the dilation distance info and divide it by the scale of the area that you're sampling in world space, you get distance information. Let's see, there we go. For more details and a better explanation with more images and code examples, Lena Paquette did a fantastic write-up. She's a programmer for Adobe, for Photoshop specifically, I believe. And the write-up shows an implementation of this specific to Unreal and Blueprints, which we converted into a C++ function for ease of use. We used it in a few different spaces on our terrain, but flatness in particular. This allowed us to basically offload the process of evaluating the terrain for flatness to the GPU, which sped it up, orders of magnitude compared to what it was initially. In the case of flatness, how we define this and what it looks like, the user can tune how much slope variation is allowed over the area that you're sampling, and the distance over which that test happens.
Let me jump in for 1 second.
Oh, yeah.
Let me just underline what you're seeing here. I was telling him earlier when we were going over the talk, it looks like a fritter to me, especially this image, and it makes me hungry. This is actually, this is one of our terrain meshes sort of extracted and just floating in space. So imagine this as like a kilometer by kilometer, and what he's showing is the flatness mass across the entire play space.
Right.
Sorry to interrupt.
No, that's okay. So as we we'll let the main big GIFs loop back, but basically we identify portions of the terrain that fall within the slope allowable area. We perform a jump flooding pass on this to give us distance field distance information, and then we threshold by those distances and any pixels on the output texture, which is projected onto the terrain here, that are white are allowable spaces, and anything else is not allowable. And I just blew through a bunch of my notes, so I'm going to try and kind of catch up with myself here. But yeah, all of this process is happening offline during our point baking process. But this allows us to expedite the process for decking in-game and again, keeping our level generation time under 20 seconds. So every potential position and candidate position for every object and asset that gets placed is already pre-verified for flatness checks.
Yeah, and I'd add too on that one that, this is jumping back to me. On that one, like every asset the environment team gives us, they make us temples, they make us these cool observatories, simple things like boulders or collections of things. That flatness, each one of those assets in that asset table, that has a required area of flatness that it needs to have be fulfilled, or it's not going to find a spot in a particular place in the map. So all of those flatness checks that Christian just went over, that's happening for every one of those assets, for every one of those 100,000 points, until it finds a spot that is satisfactory for all those rules. This is another example of some of the rules happening. This is looping over and over, but down on the beach area, which are specifically tagged in our maps as beach areas, here we have foliage that looks very different than the foliage that's down on the beach. This is just to kind of show you that we can deck certain assets in certain parts of the map using some of these rules. Of course, this requires certain information to come out of Houdini and those control maps that I talked about. This is another example. In these beach areas that are the low-lying areas, they get a different material application, but we also have a random assortment of things decking there as well. Something like this stranded battleship should only appear on the beach, but this is not like a preset location. It's also trying to find a random location, but there's only certain parts of the map that are permissible for it, such as on the beach. And so in order to make this happen, we have a set of texture maps that support the random placement. The total set are a biome mask, a control map, a height map, a normal, an ocean water map, path map, and water map. The ocean water maps, well, probably the path map is the easiest one to describe what's happening here. The paths that are set up in each map, the path map is basically coming out of Houdini and encoding the distance and direction to the nearest path. So in this way, every asset that says, look, yes, I'm tagged to be near a path and I can only be 10 meters from a path, this might be something like a street lamp. We have street lamps because the world is supposed to be a city. Parts of it are supposed to be cities that have like gone to ruin. So we have pieces of road and pieces of street lamps, things like that. Those are designed to be along paths. That would utilize the path map during the offline point baking when it's trying to determine candidate locations, determine all the places. Similar for the water and ocean maps. And this all comes out of Houdini. So I'm going to jump now into kind of the Houdini workflow. Houdini starts, the whole terrain generation process for our variants in Houdini starts with what we call the terrain paint map. We discovered during the development that when we started doing terrain meshes, they were all just generated from pure noise fields. We were taking shapes and noising them up, and then we were building up more complicated things and adding aspects. But at some point during development, it became clear that the designers in particular needed more control. This is probably the big push and pull of proceduralism, is you want to make it all random because it's cool and you can do that really easy and you love what you're getting. And then the designers or someone else says, yeah, but I want this here. And so then you have to make an accommodation for that. And then you're like, great, that's it, right? And it's like, yeah, I think that's it. That's all. I just want that there. And then a week later, they're like, oh, well, there's these other things. We obviously want those here. And so what that started to happen to us in one of our releases. It was a vertical slice we needed to deliver to the publisher, and so there was a lot of pressure at the studio to like, oh, I need to put our best foot forward, and that led to us realizing that we had to take a more of a directed procedural approach to how we were building up these terrains. And so the way we ended up going was we gave them complete control in a way, complete as in quotes. Basically, all of our terrains, and I said we had 25 variants right now, each one of these cells represents one of our terrain variants. This is a layered Photoshop file that is touched not only by tech art, but also by design, by our art director, and even the narrative team at one point was tweaking these things. These are basically, each cell has a number of layers. The green is basically dry land. The tan will be beaches. These red blobs basically are what we call POI regions. These are sort of reserved larger spaces that will make sure get flattened in an extra way so that we can put larger, significant combat POIs, points of interest, on them. So we do have fairly large structures that the environment team creates, and that's usually what are reserved for these. The final little blobs you see with the red, like egg yolky things going on, those are the boss hills. Every terrain variant has 3 boss hills. And so and then finally, you probably can't see it, but each variant has these little blue paths running through it. those are literally become paths in the terrain. So we smooth and flatten those out. And this allows the designers and the art director to look at variants and say, well, no, I want the pathing to kind of go around this thing and not go da-da-da-da-da. So basically, this is the start of the Houdini network. And this is the same file, but with another layer turned on, which is the biome mask. So you saw in the gameplay demos that we have these 4 different biomes. There's always 3 per world. This also lets the art director decide how much of each map will be given to a certain biome. And this all gets ingested into Houdini, into a typical COP legacy network, not Copernicus, because that didn't exist at the time. And the first thing it does is load this Photoshop file, which is cool that Houdini will load directly Photoshop files and you can see all the layers and stuff. I had never really played with this before, so I was very happy to discover this. It basically encodes the variant, of which we have 25, into the frame number. So if we look at frame 25, it's going to extract this with the demosaic. And now we're working only with this particular image. And the rest of this COP network is basically just separating out layers. So it pulls out the biome mask. It pulls out the boss hills. At least these are the base footprints of the boss hills. The little egg yolk inside is the top tier of the boss hills. And it pulls out things like the interior water. This is the interior water of this particular variant. I don't know if you noticed, go back quick to here. We have some pretty wacky shapes. I chose this one in particular, variant 21. I don't know if anyone noticed that looks like the Heart Machine logo. We literally threw our Heart Machine logo as one of our maps. We're so bold. Okay, so the first thing that happens in 3D in Houdini is it basically traces all these shapes and we get 2D surfaces. And so this is, in particular, it starts with the dry land surface. The first thing that happens is a kind of an extrusion. This extrusion is noise-based, but it also utilizes a thickness calculation of that original 2D shape. We were having issues where if you just, we like kind of cliffs on the side, but we didn't want tiny spurs of land, like little thin peninsulas, to also get extruded very high. So it does a calculation where it basically uses the nearest point on a particular surface and finds the nearest point of water to every point on the interior of the land surface. And then that forms a vector field that points towards the center of each landmass. And it walks that backwards to the center, kind of creates a spine, and it can measure the thickness of each landmass. And it uses that thickness to modulate the extrusion, at least this base extrusion of the mesh. So after kind of this base extrusion, I'll kind of flip back and forth between these two. So what you're seeing is it's now extracting that boss hill data, determining where the boss hills are going to live on this mesh, and basically flattening them, pretty basic. Then it builds the boss hills themselves. This subnetwork is a little complicated because these are basically this kind of layer cake boss hill algorithm that procedurally builds these kind of layer cake boss hill shapes, along with accessibility nooks that allow you to kind of get up each one. There's these ramps that will get you to the top. Those ramp positions are all based on the intersection of the paths with those shapes. So it's looking now at that path data as well. It then puts these onto the, yeah, there we go. It puts these on, it basically projects these onto the height field, working in height field at this point entirely, projects these onto the existing extrusion, and then it flattens those POI regions. I'm going to jump back and forth between previous and next. So these are those POI regions that I said are kind of reserved areas for our bigger temples and combat spaces. Yeah, basically it's kind of doing a flattening. And then water platforms. We like the feel of these kind of cliffs that if you go into the sea or in the water, you kind of have to struggle to get back out. But it was for a long time way too big a struggle that people would run out of stamina on their hoverboard. So then we came up with water platforms. It measures basically the perimeter of the entire terrain, and every X number of meters, it makes sure a water platform tries to form that will allow you to get out of the water back on a dry land. These water platforms are pretty much just prefab structures. Then it lowers the water and we start seeing the terrain kind of come together as it's going to finally look. And then we add the paths. This is maybe subtle from where you're seeing it because I don't kind of highlight them here. But as I go back and forth, this is all coming from that blue path data that we traced as well. And it's basically, We project those curves onto the terrain and then smoothing them and isolating path segments that will be too steep for the player to traverse or jump. Those discontinuities get clipped out and inform the placement of jump pads. Maybe you saw those in the game demo. The water crossings are also clipped, and those inform the placement of spanners, aka bridges. And both of those pieces of data, the spanners and the jump pads, those are an example of those things that I mentioned earlier of like PCG, like we just need these structures in the map. We know where they're going to be because it comes from the Houdini side. We know bridge needs to go here. We need jump pads along the pathing here, 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 here. Some maps have like 7 jump pads. I consider jump pads a failure because it means the terrain wasn't, the algorithm wasn't smart enough to create terrain that worked. Something I would add about this is the terrain, for our game, combat is the ultimate experience. We wanted exploration to be interesting and part of the game, but it's mostly about combat. And the designers were very adamant that we can't have a lot of slopes. So we couldn't have a lot of slopey areas because monsters track you, they run after you, and slopes are bad for combat. So we were under some interesting constraints creating this terrain that we needed to create a lot of flat areas with like small slopes or jump pads that got you from one to the other without letting them get too long. So it was interesting. It was a kind of a push and a pull. We had some cliff details. We're almost done with the network. And again, this is, as you can see, this is sort of an additive approach. It's not something really cool like erosion and all that awesome stuff you can do with height fields. And then it becomes a mesh. And we basically have caves in every level. There's one cave hidden somewhere in the map. That location, of course, is encoded in the terrain paint because the art director wanted to decide where it would be relative to other things. And so we basically do a simple Boolean to cut the cave, and then we apply materials. In this case, a different material slot is generated for each of those biomes from the biome mask. The gray area is the transition between biomes because that's a much more expensive material. So we give it a small transition zone of polygons so it's not all over the place. Let's see. And that basically gets us back to, after we generate that mesh, we then just export data associated with that mesh. And most of these are pretty straightforward. It's basically got the path information. So for every point, it can determine how far and what the direction to the nearest path is, similar for inland water and exterior water, and obviously the biomask. Is encoded with distance, so we can do interesting things with noise along the edges of biomes. And that gets us basically the end of the Houdini process. We did just do a PDG was pretty handy. We didn't use it to do like wedging because all of our random encoding was built into the frame number, as I mentioned. This is kind of the base nodes for exporting all those masks. One kind of cool thing, that checkout files at the top is a Python node. This was super handy for iteration. It basically scans that whole chain, and if you basically bypass any of those nodes, it just looks at all those nodes, says which ones are active, which ones are bypassed. It figures out, okay, what are all the maps and data that you're going to be changing, and it checks them all out of Perforce. Then you run this PDG network, and you've got basically a change list ready to check in, which is just a nice kind of like workflow improvement. And back to Christian.
So all this data is imported into Unreal for Hyperdeck to make hopefully smart choices about where to place our assets. We realized pretty early that we wanted those assets, some of which are pretty big, to feel very intentional and handcrafted. So this is an example of what a hyperfab is. So we have this central pivot rock that is surrounded by lots of bushes and smaller pebbles and even supplementary medium-sized rocks. And what is happening on screen is I'm dragging just on the X and Y axis the hyperfab around, and it's like realigning with every movement all of these different pieces with rules for things like random yaw assignments, aligning to terrain slope, stuff like that. Hyperfabs are at their core just blueprints, but with a workflow for baking, splitting, and settling that make them artist-friendly, or at least not artist-hostile. The hyperfab logic and task work was split into 2 camps. There's actor behavior in-game, like the settling logic, which is what we can see here, which is written and executed in C++. And then there is the asset creation and in-editor management logic that our environment art and design teams used, which was written in Python. I'm gonna go over both of these here as quick as I can. We're gonna go over actor behavior first because it's important to know hierarchically how these things work. Typically, if you look at a blueprint, actor, and Unreal, the primary paradigm that it follows is there's some object that is a root component, and then other scene components that are child components of the root. Those child components can also have children in a hierarchy. For hyperfabs, the idea is that the components that are the direct child of the root component are permitted to settle onto the terrain as shown in the GIF. Any components that are the children or subchildren of those components, the ones that settle, don't run any additional settling themselves, but instead inherit the transform delta enforced by the parent at the base of their respective settling branch. Settling is the act of running a line trace from some number of units above the settling component down to some number of units below the settling component, searching for a clear path down to the terrain mesh. There's a host of rules that are configurable for individual components or groups of components, which are identified by component tags in Unreal. And these run additional checks for beyond just, is there a terrain for me to settle onto, such as actor and component class, whitelists and blacklists, so that we can't have hyperfabs settling on top of each other and creating giant stacks of trees, which happened really early on and was super fun. Min and max slope ranges to settle onto, a min and max vertical delta to settle onto. So say if you have something like this rock that is settling up near a cliff edge, and then you have some ground below it, and one of the bushes traces way down below to the area below, we don't want that stuff to draw. Any of these things that fall outside of these trace conditions are culled from the final assembly and are not visible. There are additional rules that also don't serve as like placement filters, and they apply things like rotation deltas, so like I mentioned before, so like snapping to the terrain normal, hillside tangents, random yaw, and stuff like that. Height deltas for min and max z offsets if you have assets that can support that kind of vertical movement. These parameters and functions, combined with the random placement and alignment to the terrain surface, allow for a lot more randomization and in the placement of the pieces that form the POI structures as a whole, in a way that is manageable and especially iterable for artists and designers. This is another example of a hyperfab that has this center rock that is settling onto the terrain, and then a tree and some bushes that sit on top of it that don't run their own tracing because they're the child of that rock, and they just kind of go along for the ride. And this isn't just limited to, things like rocks and bushes. This is an entire city block. The camera in this shot is static, and the city block is being dragged over the terrain, and all of the individual pieces, including like, the chunks that make up the road, these pieces of buildings, which all of these like pillars and windows and staircases and stuff are all individual pieces. These are all assemblies that our environment art team put together and packed into a single actor that you can just drag around, and it just kind of works. The asset workflow, I'm not sure if this video, okay. So there's a video here that I will just walk you through, and you can pretend like you're watching it for real. But basically, the idea is that in the level, we have all these objects, and the environment art team or design team or whoever's building these organizes these and attaches different actors to like their parent components so that they can stack items accordingly. They select all of these items, and we just have a scripted editor action in Unreal that opens up some EUW, a series of EUW or editor utility widget windows that allow us to select a root component and then bake all of these actors into a blueprint, which is represented by actor equivalent components. So for things like static mesh actors, static mesh components, point light actors, point light components, etc. There were some custom actor types that were specific to gameplay that we had to create, like actor component equivalents, to try and like follow that general paradigm. There is one example of a component type that doesn't follow that paradigm that was a bit more challenging, the nav links. But that's the specifics about that aren't super important.
I would add too. Let me add here that Christian did incredible work on this. This was meant to give creative control back to the environment team. So one of the things about this tool is it was an environment team facing or artist facing tool. So all of this stuff about setting up the hierarchy and adding the component tags, we had to teach the environment team, and they were great at this. Eventually, they were all about making their own hyperfabs, packaging them up, and putting them in the game, and it was awesome.
Yeah. Yeah, the sort of impetus to start was that we wanted, trees with bushes surrounding them, and the initial implementation that we had was like data tables with like rows for a tree and then child rows for bushes, and no artist wants to go through and put numbers in an Excel spreadsheet all day. And so this was sort of like the artist friendly version of that workflow that resulted in what we have. And this is like an example scene put together with a bunch of different hyperfabs, these like rib cages with all these different pieces, the building with, a bus stop and surrounded by bushes and rubble. All of these are hyperfabs that the artists created and aligned to the terrain accordingly.
Okay. That kind of brings us to most of what we want to talk about. There's a few more details and things that we kind of glossed over. And so in a nutshell, as we say in America, that is the whole enchilada.
Enchilada.
I do want to thank Randy Reynolds, was awesome. Justin Beals, he came on, and I love, engineers are great, but I think tech art's the funnest because he was like, don't kick me out. I'm like, but you're not really in tech art. And he's like, no, I'm like a tech artist. He kept wanting to be in our tech art department, which was great. And he did amazing stuff. I didn't mention it, but there was a lot of foliage, grass and things. He wrote an entire custom, basically procedural grass system that was similar to Unreal, but much more flexible for our needs, called Grassifier. Yeah, it was incredible. Jason Keeney was our technical director, who reminded us we're shipping on the Steam Deck. Thank you for being you. I do want to add one final thing about procedural games. Besides these people that worked on this, everyone in the company had to deal with the fact that we did not have levels that were blocked out, and then the blockouts go to environment and they make them beautiful, and then you can iterate on that loop. We were basically telling them, nope, it's all random. We can't tell you where stuff's going to be. It's a crazy system that we put together that makes it all happen. And so what we found out was that proceduralism, ProcGen, was like a many-tentacled thing, and we gave it a name, the Proctopus. Respect the fearsome Proctopus. Thank you.
Good day. If you want to do a photo.